Hello everyone, this is Sir Aris. Now let us talk about um, complex infinite series and complex power series. The partial sum of a series of complex numbers will be complex numbers. So if I write the partial sums as Sn, that would be equal to xn plus yn, where xn and yn are real. For the case of convergence, if the partial sum Sn approaches the limit s equals x plus iy, as n approaches infinity, we call the series convergent. Um, this means that um, this means that xn approaches x, yn approaches y. And in this case, um, the real and imaginary parts are each convergent series. Let us consider this theorem: an absolutely convergent series of complex numbers converges. So to prove this, let's consider a stake note first of the given um, condition that there is an absolutely convergent series. So in this case, we are given that um, the sum of an absolutely convergent series of complex numbers. So we take the absolute value of the complex number. So that's an plus ibn is our complex number. We take the absolute value, that's sum of all an squared plus bn squared. Take the square root. So this series converges. Now, if this converges, we know that an, uh, the absolute value of an, is always less than an squared plus bn squared. Therefore, an converges. Similarly, bn is always less than an squared plus bn squared. I'm referring to the absolute value of bn. So, therefore, sum of all or the series containing absolute values of bn also converges. This series an and bn are said to be, so these two are absolutely, let me write that properly. So absolutely convergent series. Now, if you recall, I might have mentioned this previously, that absolutely convergent series converges. However, I have not shown the proof, so we'll prove it here. So the proof, uh, we start again that the given is that if you have a series consisting of an, so suppose the sum of all absolute values of a series an is convergent We- this means that an plus the absolute value of an is always less than or equal to 2 an. If an is negative, this is 0. If an is positive, then it's 2 an. So if you take the sum of an plus an absolute value, that's still less than or equal to sum of all 2 an. Since an is convergent, then it means that up to a certain factor, let's say 1/2 or this 2 here, then sum of an plus an absolute value is also convergent. Okay, now we take the sum of an, that's just equal to an plus absolute value an minus absolute value an, or if we write that as sum of all an, this is parenthesis, plus an absolute value minus sum of all an absolute value. These two are convergent. This simply means that an is convergent. Sum of all an is convergent. Now with that, since we go back to our previous result here that an and bn converges, so since the absolute values of an as a series and bn are convergent, then the sum an without the absolute value or the series are an and bn are convergent. Now with an and bn convergent, it means that um, the sum of an plus I bn is convergent. Again, our theorem states that an absolutely convergent series of complex numbers also converges. Let's have an example. You have 1 plus I over 2 and so on. We test for convergence. The the easiest would be if we use ratio test. So using ratio test, we have the ratio or the limit of the ratio rho as n approaches infinity of this. So 1 plus I, the next term to this, n plus 1 over 2 n plus 1 divided by 1 plus I n divided by 2 n. Okay, so this is the limit as n approaches infinity of 1 plus I divided by, this is 2n. There's a 2n that goes to the numerator. So it goes like this. And you have the limit as n approaches infinity of 1 plus I divided by 2, or 1 plus I. Actually, this already, we set n to infinity. Since there's no more n here, we can write this as 1 plus I over 2, or simply 1 plus I over 2. Now, if we take the absolute value of the terms here, that is the ratio would be just the absolute value, or the limit of the ratio is the absolute value of this. So if you take the absolute value, that would be 1 plus 1 is the real part, 1 here is the imaginary part. So you have 1 squared plus 1 squared divided by 2, or square root of 2 over 2. If you take square root of 2 over 2, that would be less than 1, which means that um, the series is absolutely convergent and hence is convergent. Another example. Test for convergence in over square root of n. If you use ratio test, what we have is, so we take the limit as n approaches infinity of in plus 1 over square root of n plus 1 divided by in divided by square root of n. So this would be the limit as n approaches infinity of in times square root of n divided by, so there's no in, just in plus 1 divided by in, square root of n divided by square root of n plus 1, or the limit as n approaches infinity of we divide this one by square root of n, that's 1 over 1 plus 1 over n. Okay, take the limit, that would give you, and here set to infinity, that is just which is 1, which means that uh, there is no conclusion. We need to use a different test. So what we can do, we expand the series. So when we expand, we have sum of all in divided by square root of n. Okay, here. That's equal to I um, minus, by the way, this starts from 1 to infinity. Okay, I minus 1 square root of 2 minus I over square root of 3 plus 1 over square root of 4 plus I over square root of 3 and square root of 5 minus 1 over square root of 6 and so on, where the real part, so those without i's, so you have minus 1 over square root of 2 plus 1 over square root of 4 minus 1 over square root of 6 and so on, while the imaginary part is 1, so this here 1i minus 1 over square root of 3 plus 1 over square root of 5 and so on. So recall that for alternating series, an alternating series converges if the absolute value of the terms decreases steadily to 0. That is an plus 1 is less than an. And the limit as n, so this should be absolute value. Okay, the absolute value an plus 1 is less than or equal to, so here there's no absolute value here, or there's no vertical line. Okay, now if we look at the real and imaginary part, they're alternating series, and the absolute value of the terms decreases to zero. So the real part and imaginary parts are convergent. So, so the real part and imaginary part are convergent. Therefore, the series is convergent. Another example, we test for convergence this series z, or the complex number z, to the power of n. So z to the n is a geometric series with, so it's a geometric series with ratio, the ratio is zn plus 1 over zn, that's equal to z, which is by definition re I theta. It converges if and only if z, the magnitude of z, is less than 1. So since the magnitude of z here is equal to r, then sum of all r and e I and theta converges if and only if r is less than 1. Now let us proceed to the next section, complex power series. We are interested in series of, so this is series of powers of z, where z is x plus iy and an are complex numbers. For example, we find the values x and y at which the series converges. Um, Again, our favorite test, we use the ratio test. So we do that by taking the limit of as n approaches infinity of the general form here, but you can take the absolute value. So that would be zn plus 1 divided by um, divided by n. Okay, and divide this by zn, or this is n plus 1 divided by n. Okay, here it seems that we are neglecting the first term, so that this ratio is still valid. So this is the limit as n approaches infinity of um, z. So this is zn plus 1 divided by zn, that's z. N plus 1 divided by n, that would be n divided by n plus 1. Or this is the limit as n approaches infinity of z 1 over 1 plus 1 over n. We substitute n by infinity, so this becomes 0, so we have absolute value of z. Okay, and from the ratio test, the series converges for z less than 1, or x squared plus y squared. So z is defined as here, x plus iy. So the absolute value of z, or the magnitude of z, is square root of x squared plus y squared. That should be less than 1. Okay, so if you make a plot of the complex plane, if this is 1, this is minus 1, 1, and minus 1, this x squared plus y squared is the interior of the terms between, oh, for x is between minus 1 to 1, okay, and for y between minus 1 and positive 1. So essentially, this condition means that x and y are inside this circle of radius 1 centered at the origin. So these points are interior of a disk of radius 1 with center at the origin in the complex plane. And this disk is called the radius of convergence, or I'll just call it the disk of convergence. Another example, find the disk of convergence of this series. So using ratio test, you get the ratio of the limit, or the limit of the ratio. Um, the general form of this is I z to the power of n, so that's n plus 1 divided by n plus 1 factorial divided by I z to the power of n divided by n factorial. So that would be equal to um, the limit of I z divided by n plus 1. Substitute n by infinity, this becomes 0 less than 1. So for whatever value of z, the series converges. For all values of z. And another example, find the disk of convergence of z plus 1 minus I divided by 3n n squared. Um, Again, we use ratio test. You have the limit of the ratio of, let's write it as z plus 1 minus I n plus 1 divided by 3n plus 1 n plus 1 squared divided by z plus 1 minus I n 3n n squared. This is simply the limit as n approaches infinity of z plus 1 minus I divided by 3. So 3n plus 1 divided by 3n, that's 3. And um, n squared divided by n plus 1. So we can write n plus 1 squared. Okay, so we can also rewrite this as z plus 1 minus I over 3. 1 divided by 1 plus 1 over n squared. Substitute n by infinity, this is 0. So you get z plus 1 minus I over 3. And for this to be convergent, we need z plus 1 minus I divided by 3 to be less than 1. The series converges for z plus 1 minus I over 3 less than 1. Or if you write that, multiply both sides by 3, you have z plus 1 minus I less than 3. Okay? Or we can also write z plus or minus negative 1 plus I. So which means that for z um, equal to, or for in a complex plane at a point minus 1 plus I as our origin, the points at which inside a circle or the disk with radius 3 centered at minus 1 plus I, that's when the series, those gives us, so those values would give us um, the the condition at which this series converges. So more explicitly, we we can also write, let's say if we use z equals x plus iy, so this is x plus iy minus um, negative 1 plus I less than 3. So this could be written as x plus 1 or x minus negative 1 plus I y minus 1 less than 3. So if we have the complex plane xy, we find, so this is our negative 1. So with x equal to negative 1 and y equals to positive 1, that's the center of our disk with radius 3. So we move up, down, left, and right 3 steps. So this 1, 2, 3. Okay, here 1, 2, 3. 1, 2, 3. And downwards 1, 2, 3. Okay, so this would be our disk. So this is our disk of convergence with center at the complex number negative 1 plus I. So the points that we need, the disk of convergence, is the interior of disk of radius 3 centered at z equals minus 1 plus I.